Welcome to the real curriculum. Another application of component of vectors in physics is in electromagnetism. So electromagnetism exists when a conductor is in a magnetic field and it cuts across the magnetic field lines, which is the magnetic flux. So the magnetic field lines is also known as the magnetic flux. And from Faraday's law of electromagnetism, the rate of change of magnetic flux is proportional to the voltage across the ends of the conductor. So the idea is that the conductor would cut across the magnetic flux and vary in the extent to which it does that, meaning that there should be a motion involved. Either the conductor moves in that magnetic field or the magnetic field moves as per the magnet moves. So the idea is that the conductor is supposed to cut across magnetic field lines to create a rate of change, to create a change which will now be measured by the rate at which it happens, which will now be proportional to the voltage across the ends of the conductor. Alright, so the magnetic field lines, also called the magnetic flux, is given by this Greek alphabet phi, measured in Weber, according to the name of the person. Then somebody called Weber, forgotten his full name, Weber. So another quantity is the magnetic field line density, that's magnetic flux density, measured in Tesla. Another person that is common, Tesla. So the magnetic field line density, that's the magnetic flux density, is equal to the magnetic flux over the area of this conductor that the magnetic field affects, the area of the conductor's surface in the magnetic field. So the force of the electromagnetic force through this conductor is given by the magnetic flux density times the current through the conductor times the length of the conductor in this magnetic field, as opposed the situation where the conductor is inclined in the magnetic field, in the magnetic field. So let's say it's inclined at an angle theta. The force is going to be equal to Bi and the component of the length of this conductor in this magnetic field that is in the direction as when it was like this. So if we draw our vector diagram, we know that the length is like this in this case. The field direction is this, then this represents the direction as when it was like this. So we want to find the component of L when it was like this. That's the component of L in this direction. So this is our angle theta. So we know that since this direction is making the angle theta with the vector L, then it is the cos component, while this other one that is perpendicular to it is the sine component, and that's what we're looking for. So automatically we take our sine component. So the electromagnetic force is given by this from what we've done already. Then in this case, the conductor is at 90 degrees to the field, so it's perpendicular to the field. So we notice that we're giving the value for the charge instead of the current and its velocity. So we'll do some derivations here. We have our magnetic field density, magnetic flux density, also called magnetic field induction. So we have it already. So B is given to us. We don't have our I, we don't have our L. Instead, we're giving charge and velocity. So we'll do some derivations. We know that the velocity is equal to the length over the time. So we also know that the quantity of charge is equal to the current times time. Current times time. So current is going to be equal to the quantity of charge over time. So if we replace that here, we'll have Q over T. We have L sine theta. Then we know that L over T is the velocity, L over T. So we have L over T, which is the V, sine theta. So I think we have everything we need now. So we'll go straight to finding our force. We have 5 exponential minus 4 times 10 microcoulombs. That's 10 exponential minus 6. Then our velocity is 1 exponential 5 times sine theta is sine 90. So we have sine 90, which is 1. So we have sine 90. Because of it is perpendicular, which gives us 1. So 5 times 10 times 1 is 50. Then 10 raised to power minus 4 times 10 raised to power minus 6 times 10 raised to power 5 is 10 raised to power minus 4 minus 6 plus 5 from laws of indices times 1. So we have 50 times 10 raised to power minus 10 plus 5. And that will give us 50 times 10 raised to power minus 5 Newton. So putting in standard form, we'll have 5 times, so we'll have 10 for 50 times 10 raised to power minus 5. And that will be 5 times 10. 10 here has power 1, so we have 1 minus 5 Newton, which will be equal to 5 times 10 raised to power minus 4 Newton. And that's option B. So these are things that would most likely not be told to you in school. So like and hit the subscribe button, so I'll be encouraged to do more for you in particular. Thank you very much.